Hello everyone, I'm Dr. Emilia Bertolo and I'm a principal lecturer in chemistry at Canterbury Christ Church University in the section of Natural and Applied Sciences. This is the first of a series of videos dedicated to kinetics. Kinetics is the branch of chemistry that studies the speed of reactions. At the end of these videos, we're going to discuss quite a few key concepts. We're going to discuss some key kinetic parameters, what the rate of reaction is, what activation energy is, some key concepts that you will come across if you study this topic. We're also going to look at what factors affect reaction rates. How can we make the same reaction go faster or slower depending on various issues, the state of the reagents, etc. We're also going to do some simple kinetics calculations using reaction rates. We're also going to be talking about something called equilibrium, which is that we typically, when we talk about a reaction and we think about reagents and products, we always kind of assume that the reagents will react completely to make the products. However, that is not always the case, and we'll discuss when those cases are not. Any reaction can reach what we call an equilibrium state, and some of them will reach it easier than others. A state in which the reagents react to form the products, and the products are in sufficient quantity to start reacting back to form the reagents, the initial reagents. So you end up with a sort of a standstill, and the reaction goes forward as fast as it goes backwards, and it looks as if nothing is happening, but actually it is happening. The reaction is happening all the time, just backwards and forwards, and with at the same speed. And we're also going to look at what we can do to get out of that equilibrium position, that sort of being stuck in the reaction, going backwards and forwards at the same speed. How can we typically make more product when our reaction is in that equilibrium state? And we call that using the Le Chatelier's principles. Le Chatelier was the French chemist that came up with this principle. As usual, I've divided the content in several videos to hopefully make it easier to follow. And if you have any questions, just drop me an email and we can organize a tutorial. Let's make a start. So I showed this slide when I was starting the videos on energy of reactions, the thermodynamics. And it's the link between thermodynamics, kinetics, and equilibrium. And it is these questions that we as chemists ask all the time. And thermodynamics, kinetics, and equilibrium help address those questions. So if you have a generic reaction in which you have some reagents that react to make some product, one question you might want to ask yourself is, will this reaction actually happen? If I mix those reagents in a conical flask, in some sort of vessel, will they actually react? And how can we answer that? Well, thermodynamics help us answer that because we defined a function called Gibbs free energy and the change of Gibbs free energy that we call delta G. And that delta G, that value of that Gibbs free energy, the change in Gibbs free energy between the reagents and the product side, will tell us if a reaction will happen, if it will be spontaneous. If that value of that energy function is negative, then the reaction will be spontaneous and you will not have to do anything to make it happen, it will happen. If delta G value is positive, then the reaction will be non-spontaneous and will not happen. If you want it to happen, you will have to do something about it. Typically, use heat. So that's our first question. Will the reaction happen? Well, when we look at the reaction and we wonder, will this happen or not? Well, the first thing we look at is delta G value. If it's a negative number, yes, the reaction is spontaneous. If it's a positive number, then no, the reaction will not be spontaneous. And that thermodynamics help us answer that. Another question that you might want to ask yourself is, if the reaction happens, as if it's spontaneous, will it release or absorb heat? And again, thermodynamics gives the answer to that question, and it gives us the answer to that question by looking at a particular function called enthalpy. the changing enthalpy of a reaction. And it tells us basically how much heat will be absorbed or released when the reaction happens. So if it's a negative number, then this reaction will release heat, and we call that an exothermic reaction. And if the value of delta G of the changing enthalpy is a positive number, then the reaction will be endothermic. And again, thermodynamics help us answer that question. Will the reaction happen? We look at the delta G value and we know if it will be spontaneous or not. Will it release or absorb heat? Well, we look at the delta G value and it will tell us if it's exothermic, will release heat, or endothermic, if it will absorb heat. So thermodynamics tells us if a reaction will happen and if or not, if it will be spontaneous, and if it will release or absorb heat. What it doesn't tell you in any shape or form is when will it happen. Will it happen in a few seconds, in a few minutes, in a few days, weeks, years? How fast will it happen? Nothing in thermodynamics tells us how fast a reaction will happen. It tells you it's going to be spontaneous and it will absorb or release heat, but not how fast that's going to happen. And because that's not the role of thermodynamics. To find out how fast a reaction will happen, we have to look at the speed of the reaction. And that is the role of kinetics. So kinetics is all about how fast a reaction goes, and how can we make it, typically, how can we make it go faster? Or if it's an undesirable process, let's say, for example, the degradation of a pharmaceutical drug, how can we make it go slower? So how can we control how fast it happens? And what factors affect the speed of a reaction? And finally, there is the issue is what happens if a reaction gets stuck? What happens if you mix the reagents and they start reacting and you make products, and at some point after a little while, there are enough products in the medium and they are not that stable with respect to the reagents, and they start reacting with each other to give you back the reagents. That's what I mean when I say it gets stuck, and we call that equilibrium. And it is a part of thermodynamics to a certain extent, and maybe with a touch of kinetics, that is all about a reaction that is stuck, and the reaction, the speed going forward, the speed from the reagents to the products, and the speed going backwards from the products to the reagents is the same. And so you are stuck in what we call a dynamic equilibrium with a certain quantity of reagents and products. And how can we actually get more products? How can we get our reaction going so it will reach another equilibrium position, but it will have produce more products in the process? And that's what equilibrium talks about. What affects how fast our reaction goes? Well, the first point is the physical state of the reactants. So for reactants to give you products, they might come in contact with each other. They need to collide, they need to touch each other, bonds need to be broken and other bonds made. So the more they collide, the more rapidly they will react. So when you have reactants in solid, liquid, or gas form, they will react at different speeds. In gas form, the molecules are not attached to other molecules by intermolecular forces. They are free, they are moving around, and they are more likely to collide and give the product. In liquid, you have a few intermolecular forces, so those molecules are slightly more less free to move because they are held together in a liquid form by intermolecular forces, and they will be more difficult to find other molecules of the other reagent to react. And then you have a solid form in which the molecules are very tightly together with many intermolecular forces, and that's more difficult. They need to break those intermolecular forces to be able to react with the other reactant to produce the products. And even in the same form, for example, in solid form, it means It makes a difference if you have large particles or very fine powder. Again, the finer the particles of the solid, the more surface area they are, the more free they are, the molecules to react with the other reagent. The concentration of the reactants also plays a role, an important role, because typically, the more reactant you've got, the more likely it is to collide with the other molecules of reactant to give you the product. So there are more collisions. The molecules of the reactants collide with each other, and if you have more molecules of reactants, then you will increase that possibility of those collisions, and that some of those collisions will be favorable, and the bonds of the reactants will be broken, and the bonds of the product will be made. Temperature is also helpful to increase the speed of a reaction, because when you increase the temperature, you're giving kinetic energy to your molecules, so they move faster, especially if it's a gas form. That affects really gases. So they move faster, they move more, they are more likely to collide, effectively and break the bonds between the molecules of reactants and make new bonds, which are the molecules of the product. And as a rule of thumb, 10 degrees increase in temperature doubles your reaction rate. You have to be mindful of the temperature, because it might be that your reactants or your products are not stable at particular temperatures, so you cannot play with temperature for forever. You might have some limitations how stable those chemicals are. But assuming they are stable at the temperature you are using, when you increase the temperature, the reaction rate increases. And the use of catalysts, either man-made catalysts or enzymes which are naturally biological catalysts. Those are agents, it can be chemicals or it can be enzymes, that increase the reaction rate, but they are not themselves part of the reaction. What they provide is a mechanism to facilitate those collisions between the reactants. So they don't participate in the reaction as reacting themselves, they are not consuming the reaction, they are there to facilitate the reactants meet each other, collide more effectively, and increase your reaction rate.